Ron here. I bought a mini oscilloscope from jyetech.com, and I'm going to use it to see what the Joule Thief waveform looks like when it's in operation lighting a small LED. So let's take a look at this guy first. It's model number DSO062. If you look up www.jyetech.com, there's a series of small affordable oscilloscopes that they sell there. They're very good. They work as advertised. And I have a Joule Thief on the table, and I'm going to be measuring the waveform of that Joule Thief. It starts off with a toroid. That's a gray 1-inch toroid. Model number is 55894-A2 for people that are really interested. I have used magnet wire, bifiliar, wound 20 times, gauge 28. So that's 28 gauge wire wound 20 times. Bifiliar means there's 2 filaments wound together around that toroid. And if you don't understand how to make a Joule Thief, just look up Joule Thief on the internet. There are scads of people that are making them. The transistor that I'm using is a MJE 181. Any small signal transistor, NPN type, will do. The resistance I'm using at the base of that transistor is a 1.5 kilo ohm resistor, and in parallel with that resistor is a 0.1 microfarad capacitor. The light I am lighting is a typical 5mm LED. The LED is situated between the collector and emitter of the transistor, and I have an oscilloscope probe attached in parallel with the LED because I want to see the waveform as it travels through the LED. I want to see the waveform at work from this Joule Thief lighting that little light as if it were a flashlight. And in keeping with the flashlight theme, I have several batteries down here, and they vary in voltage from 1.8 all the way down to 1 volt. So I have 1.8, 1.6, 1.4, 1.2, 1 volt, and I'd like to see if I made a Joule Thief flashlight as the battery wears down, what happens with the waveform, how efficient is it at driving an LED light, how long will it last. And I'll look at other parameters too. And I'll be measuring the amount of energy that's being used from the battery by using a milliamp gauge. And I'm going to take snapshots of my oscilloscope and show that all to you later on. But right now I'm going to hook up the Joule Thief and let you see the waveform yourself. I'm going to use the lithium battery, which is a high energy battery. It's coming in at 1.8 volts. So I'm going to start up the Joule Thief, and there's a lot of light in here, but you can tell the LED is lit. Joule Thief is working. It's running. And what I'm going to do now is just connect up my probe to the oscilloscope. I know you can't see it from where you are, but I'm going to press a capture button to take a picture of what the oscilloscope sees, so I can just unhook my Joule Thief. And if I can get this close to you and hold it steady, you can see the waveform of a Joule Thief in operation right across the LED. This one is coming in at about 4 volts output across the LED, and you can see that the waveform has a large foot at the bottom. It looks like it's above 50% duty cycle. That is, it looks like it's on more than it's off, and that wave shape looks to be trapezoidal. And I'm using a 1 millisecond time scale here. Each of those rows represents 1 volt. So you can count up 4 volts from the foot. It's almost 4 volts in output. So that's pretty cool. Let me erase that waveform off of there. And I'll do that just by unplugging it for a second, letting it boot back up. Let me move over to a weaker battery. Let's move right down to the 1-volt battery, see what that looks like. And again, I'll have snapshots of all this later on. The 1-volt battery manages to light up the LED quite nicely. It's using far less amperage than the high voltage battery. And again, let's just connect up our oscilloscope for a second. Hit the capture button on the same time scale. And let's take a look at what this waveform looks like. Not sure if this is coming across, but this waveform is about 3.2 volts to the peak, and it looks more like a triangle than a trapezoid. And it's off more than it's on now, so the duty cycle is quite low. It's not 50-50, it's probably more like 35% on. So the waveform changes, but the circuit struggles to keep that LED lit as the voltage goes down. So let's go to the computer and look at some snapshots that I've enhanced. Perhaps you can see those better. I'm not sure if this is going to come across in my camera. Alright, here are the waveform snapshots off my oscilloscope of the Joule Thief being run with an input of 1 volt. And you can see that the peak is about 3.2 volts. I'm going to run through the battery voltages quickly and just change the waveform so you can see how they changed as energy increased into the Joule Thief. So this is the waveform output across the LED at 1 volt. Here it is at 1.2 volts, 1.4 volts, 1.6, and 1.8. So as the energy increases on the input, it also increased the voltage on the output. Also, we noticed the waveform got fatter. The more energy was fed into the system, the fatter the waveform got, and also the duty cycle became more robust. Let me show that in reverse now. This is the highest level, 1.8 volts in, 1.6, 1.4, 1.2, and 1 volt. So let's go look at the actual numbers and see what that means. Well, here are the battery input voltages from 1 to 1.8. You'll notice that as the battery wore down, less energy was consumed by the circuit or drawn into the circuit. The output voltage also went down as the input battery voltage went down. Went down at almost the same rate. You'll also notice that as the power ebbed away, the duty cycle got smaller, and at the same time the duty cycle got weaker. That it was, I should say, the circuit was on less than it was off. The speed of the circuit also increased, the speed of the pulses. So that's an interesting phenomenon of the Joule Thief. Now if you look at the voltage that was supplied and the voltage output, if you look at it as an addition problem, the Joule Thief tried to add 2.1 volts from the input to the output. So if you add 2.1 to each of these, you nearly get what is output at the other end. So that is interesting. Now, as a last item, I have included this 3 volt addition to this list. The 3 volts were a 1.4 and a 1.6 volt battery connected in series. So this is a straight DC 3 volts traditional circuit, and it drew in as much power as the 1.8 battery did alone. So it drew in more power than the Joule Thief would, say if it was at, well, let's say that it's equal. It drew in as much power as the Joule Thief did at its highest. And let's say that it ebbs away at the same rate and uses less energy as the battery powers decrease. the mere fact that the DC circuit needs 2 batteries to operate as opposed to 1 battery at a time. The Joule Thief wins the contest by virtue of it will run twice as long, because you can use 1 battery instead of 2 to get the same result. Man, see you later.